Thanks for the introduce. Good afternoon, everyone. I'm Qiuyu from Tsinghua University. Today, I'd like to present our work, milliMorph. This work was done when I was visiting Tangible Media Group, collaborating with Jifei, João, André, Professor Haipeng, and Professor Hiroshi. Okay, before I talk about our work, let's look into nature first. As you can see, there are many kinds of microfluidic systems, such as the hydraulic actuation system in insect wings. This small-scale pneumatic or hydraulic system can be very quiet, efficient, and have many unique properties. In fact, the microfluidic technology has already been widely applied to the field of biological or chemical analysis. Now let us look back at the fluid-driven shape-changing interface for HCI. There was shape-changing soft composites made through molding and casting process, and later rapid fabrication through heat sealing was proposed. Utilize such rapid fabrication methods, directions like furniture scale or rigid inflatables, or hand scale or human scale inflatables for haptic feedback were investigated. While all these projects are focused on inflatable structures that are at centimeter to meter scale, with milliMorph, we focus on fabricating arrays of millimeter scale channels and chambers. And our results show that milliMorph brings many new design opportunities that are unique at small scale, which we believe could expand the design space of the current fluid-driven shape-changing interface. Okay, in the bottom of this slide is a collection of some standard milliMorph samples we made. Before we talk about the new opportunities, I'd like to give a brief introduction of how we fabricate milliMorph. Since the actuation force of millimeter scale chambers is relatively small, we chose the very thin and lightweight PT film, which is 20 micrometer thick. Traditionally, in the heat sealing process, the heating tool is pressed against the substrate. However, if you want to get sub-millimeter wide welding seams, a needle-like heating tool can easily scratch or even penetrate the very thin film we use. So we developed a non-contact hot air thinning method. The pressurized hot air flow pushes the two layers of thin films against each other and has the film sealed without no surface damage. Based on our test, the film can be as thin as 0.2 millimeter. So in the left is the footage of sealing the clear film and the metallized film. You may wonder why we want to seal the metallized film. Well, we think that sensibility is crucial for making an interactive and responsive interface. And we noticed that the PT film coated with aluminum was widely available at a low cost. In fact, many helium balloons for parties are made from this kind of material. Though the metal coating is very thin, usually 40 nanometer, we found it's conductive enough for making circuits. So after the film is sealed, we have it masked robotically or manually, then etched, and finally cold soldered with conductive ink. Compared to add another layer of soft circuits, this approach won't compromise the softness and the lightness of milliMorph. Now back to the new opportunities. The millimeter scale chambers enable three novel aspects of shape change. And since the small chambers require very small volume of medium to actuate, they can be driven by liquids with low energy consumption. This allows us to explore actuation mediums other than air, like water, sensitive resin. And the embedded circuits give milliMorph sensing abilities. And at last, milliMorph can be actuated through multiple approaches, electrically or non-electrically. To be specific, as a left As the left figure shows, the smaller chambers make it possible for smoother shape change, and also, of course, high-resolution texture change. And as I mentioned before, the small chambers require little amounts of air to be inflated. This enables the chambers to be actuated at a very high rate, compared to the larger scale chambers in prior work. To evaluate the performance, we designed a test to measure the bending curvature of a standard sample when it was actuated under different frequencies. The results show that the sample is quite responsive below 10 Hz. Well, this test was carried out at 2 bar, and the sample is connected to a very thin needle. Actually, the sample can be very responsive 20 Hz or even 30 Hz if it is connected to a thicker needle or tube. Besides, at sub-millimeter scale, the flow resistance will dramatically increase when the diameter of channels is decreased even slightly, which will greatly slow down the flow rate. This allows us to control the shape changing sequence by changing the width of the connecting channels. In this footage, the width of the narrower channel is around 0.0 millimeter, and the width of the wider channel is around 1.5 millimeter. In this case, we don't want the chamber to be filled too quick, so we use water to actuate it rather than air. Okay, the embedded circuits make it possible for milliMorph to be actuated quietly through electric heating. The sample in the left footage has low boiling point liquid inside and resistive heater etched. As you can see, it is simply powered by 2 button batteries. We also have successfully fabricated sensors like the slider and the button milliMorph. These new design opportunities can be combined to create novel applications. Like in this example, in the middle of the robot are chambers that act as muscles, and on the wings there are some seams that act as at the wings to reinforce the thin film. The mini robot can flap at 10 Hz, which matches the living butterfly. However, due to the weight of the tube, it cannot really elevate for now. This is an example of the reversible 4D fabrication. The 2 flowers in the footage have the same design of chambers on every petal, but connecting channels are carefully designed in order to have the channels filled in a certain sequence. So the flower will either fold like rose or lily. And of course, the sequential folding can also be fixed with photosensitive resin injected and UV light applied. The thin-soft milliMorph film is quite conformable to other surfaces. It can be applied to act as a haptic feedback layer. For example, you can add it to the internal surface of a latex glove. And if low boiling point liquid is injected, this haptic layer will change texture when the user touches something hot, thereby providing a haptic alert and better thermal insulation, because the medium is turning to gas phase. Maybe you can also use this in haptic feedback in VR, right? And with low boiling point liquid injected and circuit etched, milliMorph can be actuated without a noisy pump. We can make responsive variables, such as a bracelet that show buttons when needed. The bottom layer of the bracelet is etched with heating circuit, and the top layer is etched with two touch sensors. The function of the buttons can be customized according to the scenario. Like you can use the buttons to answer the phone and then hang up. For now, the prototypes connect to external power source and the control board. But small customized battery and the control board can be integrated to make it actually portable. When response to environmental heat, milliMorph can be a self-contained shape-changing interface. Here we show a bunch of stickers that can remind people to avoid scold in kitchen. The small size of chamber and the big surface area to volume ratio allow the sticker to respond and revise quickly, even when it is driven by the phase change process. And there are many other kinds of low boiling point liquid that can be injected to help the sticker respond to different temperatures. You may notice we use the metallized film in this to make these stickers. Well, in this example, we didn't really etch any circuits on them. Metallized film is used mainly to make the stickers fit in the kitchen elegantly. While milliMorph has exciting potential as a shape-changing thin film material, there are also limitations and space for improvement. Here I list several directions. For now, all the samples are fabricated with one-layer structures. We'd like to try multi-layer structures in the future. We'd also like to try thinner film, which may make on-skin pneumatic shape-changing interface possible. And it will be very interesting to explore more mediums for actuation, or even develop embedded in actuation source, maybe with some sort of chemical reaction. Yeah. So that's milliMorph, the fluid-driven thin film shape-changing materials fabricated in millimeter scale. Thanks for your attention.
Questions?
Would you say fluid? Have you tried like a ferromagnetic fluid that you put a charge and change the viscosity to maintain a shape versus not?
Sorry?
Using a magnetic fluid to change the viscosity?
Uh-huh.
Have you experimented with that?
We haven't do that. For now, we use water to control the sequence, and we test test the resin. We haven't tested other kinds of liquid yet.
Any other questions?
Hi. I just would like to check the novelty of the low boiling point liquid inside of the film.
Yes, I think there's prior work that use low boiling point liquids. You see the phase change process is kind of slow compared if you actuate it with pump. But if we have the millimeter scale chamber channels, the response time and reverse time can be much shorter, compared to a prior work. So I think it kind of make it, more practice when driven by the low boiling point liquid. Yeah.
So it is 12:30, so we're going to end right here. If you have questions, come talk to the speakers at the front. Otherwise, have a great lunch. Let's thank all the speakers again.
Thank you.